Okay, hello everybody. Thanks for coming along to the seminar. We're delighted to have Michael Arntzenius, of course, PhD student in our group who's writing up in his fourth year now, supervised by Neil. And he's going to be talking about something that I don't immediately remember because he changed his title. He's not showing his screen. Why don't you show your screen, Michael?
Yeah, why don't I share my screen?
See the title.
All right.
Great. So, Michael, you're going to tell us about monotone fixed points and a variety of related things, I guess. Far away.
Yeah, sorry, I didn't have a title on the slide, but it is the things I'm going to talk about. First, I'm going to introduce monotone fixed points and some examples of things they're good for, and briefly talk about DataFun, which is a language I'm working on built around the idea of computing monotone fixed points. And then I'm going to discuss two ways to try and make them go faster. The first is to try and incrementalize these fixed points, and the second one is to try and compute them concurrently. And unfortunately, I don't know how to do both of these at the same time, but I'm going to give the talk anyway and hope that some people have some useful feedback on that point. The first two bits are published work. The concurrent fixed points is much sketchier. And I may not even have enough time to talk about it. We'll see. So first, what are monotone fixed points good for? Well, they're good for computing a wide variety of things. You can compute graph reachability with them, which is the simplest example and will be the running example we use throughout this talk. But you can also compute things that are probably more interesting, like finding which substrings of a string match a regular expression, or, and this is probably the widest use in industry, doing abstract interpretation of large programs for static analysis purposes. And the way that you can do that is, at least in principle, you can just take the function you're trying to compute the fixed point of and iterate it. And we'll see an example of that later. But for now, I'm going to focus on graph reachability because it's the simplest example and easiest to explain. And I'm going to show you how you would express reachability in a graph in one of my favorite languages, which is Datalog. And it's very simple. Datalog is a logic language. So you just say what you mean. This means that the start node is reachable. And this tells us that a node y is reachable if there's some reachable node x, which has an edge from it to y. And this is very nice and concise. But Datalog does have a slight problem, which is that it can't really abstract over code like this. And so if you have many different graphs and you want to compute reachability in each of them, you need to repeat yourself many times. And this is annoying. If I was a mathematician, I would just sort of say, look, there's a function, there's a reachability function. It takes a graph represented as a set of edges. It takes a start node, and it produces the set of nodes reachable from that start node. And it finds that as a fixed point of this function. And this function tells us that a node is reachable if it's the start node, or if there's a node x that's reachable and an edge from x to y. So this is the same program written differently. So as a language designer, I look at this and say, okay, this is mathematics. What would it take to turn it into runnable executing code? And so we're going to design a language to do exactly that, or rather, we have already designed a language to do that. First off, we have lambdas in here, we have functions, so we're going to need a lambda calculus. So we'll start with a simply typed lambda calculus. We also are manipulating sets. Let's restrict ourselves to finite sets since we know how to represent those on a computer. Infinite sets are a bit more difficult. Let's not worry about them. And for manipulating these sets, we'll use set comprehensions. And we know how to turn those into loops because they're just monadic comprehensions. And we know how to do unions over sets. Oops. We also are using a fixed point operator. It's a little less obvious how we're going to implement that. Put a pin in that, we'll come back to it. And also, one of the justifications for this fixed point existing at all is that the function we're trying to take the fixed point of is monotone. It's very easy to come up with functions that have no fixed point if they're non-monotone. What's the fixed point of the negation function on Booleans? It doesn't have one. So to ensure that the function we're taking the fixed point is monotone, we're going to do a very drastic thing. we're going to insist that all functions in our language are monotone. To make sense of this, our types will be interpreted as partially ordered sets. And this is going to work out for us because if you take two monotone functions and compose them, you get another monotone function. So if all of your built-in functions in a simply typed lambda calculus are monotone, every definable function will be monotone.
Does this mean that Booleans, for example, are not a legitimate type?
Booleans are a perfectly legitimate type. They're ordered false less than true.
Ooh.
Yes. So
Okay.
in fact, there are two Boolean types, really.
Yes.
There's false less than true, and there's false incomparable with true.
And maybe there's true less than false.
Yes. That one has fewer uses because it's isomorphic to false less than true. So you may as well just swap the names.
Oh, when you say isomorphic, though, I mean a function which is monotone with respect to one order is not with respect to the other.
Yes.
I mean, it's anti-monotone.
Yes, that's correct. In the programs that we've actually written in DataFun, we've not found much use yet for anti-monotone functions. I do have some work on accounting for them, but for now, let's just worry about monotone things and non-monotone things, which is the next thing I was going to talk about. Because monotonicity is great, but it should be clear that there are useful functions that are not monotone. So if every function is monotone, how are you going to handle those functions? And the way we do this is we can internalize non-monotonicity into a monotone world. And we do this with a comonad called box. And it's worth spending some time explaining how box works because it's going to be relevant later. And it's specifically relevant to the difference between Booleans false less than true and Booleans false incomparable to true. So what box A is...
Sorry, just before you go to box, can you just say that do you have a fixed set of types built into the language, or do you have a way to define new types, and then you'd have to also have a way to give the ordering on them?
We basically just have a fixed set of types built
Okay.
in. They include sums and products too.
Yeah.
Yeah.
Fine. Thank you.
Yeah. Oops. So box A is defined as the same set of values as A, but with a different ordering on them. And the ordering on box A is discrete. So x is below y, x is less than or equal to y, if and only if they're equal, which is a very boring order. Nothing is less than or greater than anything but itself. And this boring order has a very useful property. Every function out of a box type is monotone. Doesn't matter what it does, because it trivializes the monotonicity condition, right? X is only below y, inputs are only growing if they're staying the same, and therefore the outputs must also stay the same. So if x is equal to y, obviously f of x is less than or equal to f of y. So this is how you internalize non-monotonicity into a otherwise monotone world. So now armed with this understanding of box, let's take a look at our math example, how we wrote reachability in math, and see what it takes to turn it into running code. So what it takes is we need to annotate a few things. We're not going to assert that this function reach is monotone, so we're going to box its arguments. That comes along with some term annotations. We have to put square brackets around some things. I'm going to ignore those. This talk is not going to be about the typing rules in DataFun and how monotonicity is tracked. And we also, in math, we just use the same variable twice to declare equality. In DataFun, you have to be a bit more explicit. You have to use an equality check. And that's it. This is now runnable code. But how does it run? Right? I'm using this fixed point operator, and I put a pin in that. Well, the easiest way to evaluate fix is to just iterate. So let's take a look at the function that we are trying to find the fixed point of. We're trying to find the fixed point of this step function, right? That says the start node is in there, and if x is in the reachable set, and there's an edge for x to y, y is in there. And we can iterate this function as follows. Initially, we set the first iteration to the empty set, and then every subsequent iteration is step applied to something. And if you do that on a simple line graph, you'll get a sequence of iterations that look like this, right? Initially, you'll discover that the start node is reachable, and then at every subsequent step, you'll expand your set of reachable nodes to include its neighbors. And this is simple, easy to implement, it's clear why it works, and it is terribly, terribly inefficient. And the way to see that is easy if you just look at node number 2 here. We discover it's reachable in the second iteration because the start node was reachable in the first iteration, and there's an edge from the start node to the second node. We rediscover that it's reachable in the third iteration for the same reason. The start node was reachable, and there's an edge out of it. And we rediscover in the fourth iteration. And if we had more iterations, we would keep rediscovering it. We do this redundant rediscovery a number of times proportional to the number of iterations we take, which in this case is proportional to the length of our line graph. And you can see that the work being done here is actually quadratic, because just sum up the area inside the colored lines. It's a triangle, and if the line graph were larger, it would be a bigger triangle. So as humans, we know that we can do this in linear time, right? How would we do that? Well, we'd find the frontiers. And at first, that seems like it's a graph-specific insight. But let's press on a bit and see whether we can write some code that would discover these frontiers, right? So the frontiers are sort of, the first frontier is a gimme, it's just the start node, right? And then the next frontier, right, the set of nodes adjacent to the things in the first frontier, well, it's the set of things adjacent to something in the previous frontier, right? So I'm calling the frontiers dr sub I for reasons that will become clear shortly. And so the next frontier, dr sub I plus 1, is going to be all those nodes y, which have an edge into them from something in the previous frontier. Now, why am I calling them dr sub I? It's because they're actually the differences between the iterations over here. Dr sub 1, for example, is the difference between R1 and R2. If we union R1 and dr1, we get R2. And this is how you actually generalize this idea to apply to more than just graphs. What you're computing here are not necessarily frontiers, they're the changes between your iterations. So what you need to generalize this is a theory of changes for a higher order language. And by only computing the changes between iterations, we don't have to do all this redundant work. And this strategy of only computing the changes between iterations is what's called in data log semi-naive evaluation. And we've known how to do it since the 80s. But data log is a first order language. To generalize it, we need a theory of changes for higher order languages. And so to do that, I'm going to build on prior work on something called the incremental lambda calculus. As we've applied the incremental lambda calculus in DataFun, what it means is that every type gets associated with a type of changes, delta A, which represent the possible changes to values of type A. And to formalize this, we give a little relation that says the change dx of type delta A turns the base point x of type A into the output, the updated point y of type A. So what are the changes possible?
Wait, sorry, I'm a little lost. So what's this colon subscript A and the wiggly arrow again?
This is just a funny notation for a ternary relation.
Oh, it's a ternary relation between dx, x, and y.
Exactly, yes. It's a relation that says this base point, x, when you apply dx to it, produces the updated point y.
Okay, and so x and y have type A and dx has type delta A.
Correct.
Okay. Oh, sorry. Thank you.
Yeah. Perhaps I should have put this first.
Sorry, I was just doing left to right parsing. Beg your pardon.
Yeah, no, fair enough. Yeah.
This construct called where, Simon, you know.
yeah, I know. No language can have that.
All right. So what are the changes to sets? Well, remember, our purpose here is not to handle all possible changes. It is to make fixed points faster, and our fixed points are monotone. Our iterations increase until they hit the fixed point, which means that we only need to handle increasing changes to sets. The way a set grows, right? So the way we order sets, by the way, is by inclusion. A set is smaller than another set if it's a subset of it. So the way they grow is by gaining more elements. So a change to a set is just the set of things you added to it. And our relation will say exactly that, right? That the change dx applied to the base point x gives you x union dx. And we can now go through, all the other types in our language. I won't go through all of them, but I'll go through some examples and figure out how they change. Pairs, for example, a change to a pair is a pair of changes. This is pretty straightforward. If you have a change from the first half into the updated first half, dA turns A into A prime, and dB turns B into B prime, then the pair dA dB turns the pair AB into the pair A prime B prime. More interestingly, or perhaps more boringly, what are the changes to our box type? Well, our box type, remember, represented non-monotonicity, and it ordered things discretely such that nothing was less than or greater than anything else, which means there are no increasing changes possible. The only change possible is to remain the same. So there's only one change at type box A, and its effect is to keep things the same. And so this is interesting because in the monotone world, box A represented not being monotone. And in the world of changes, box A represents not changing.
So one and unit, is that just a typo?
One here means unit.
Okay.
Yeah. Oops. Right, but this is supposed to be a higher order functional language. The most interesting thing, of course, is what are the changes to functions? And so the change to a function is going to be another function that takes the original input and is boxed for reasons that I won't explain. This is what makes it work, what makes the sort of monotonicity work. It takes the original input, it takes a change to that input, and it produces the change in the output. So to make that more formal, right, what is the relation, right? When is df a valid change from f into g? Well, it's going to tell us how to incrementalize function application. So df is going to be a valid change from f to g if, when I give it a change to the argument of the function, turning x into y, it tells us how to turn fx, the original function applied to the original argument, into gy, the updated function applied to the updated argument. And we do that by just applying it to the original argument and to the change to the argument. And so this is the definition of our change relation for function changes. All right. Oops. All right. Now let's look at an interesting or possibly boring special case of this relation. What if df is turning f into itself? In other words, if df is a non-change or a zero change. It may seem like this is boring, but although it doesn't change the function, we are still allowed to change the argument. And so what df then says is it tells us how the output of f changes as its input changes, which is interesting because that's exactly what we needed to incrementalize our fixed points. We were iterating a step function, so we were repeatedly applying it to a growing input, and we wanted to know how the iterations, how the outputs of the step function were changing. So in this case, for a change from a function into itself, we call df the derivative of f because it tells us how f changes. And derivatives are exactly what we need to compute fixed points faster. So to see how we do that.
Sorry, can I ask about the previous slide?
Yeah, this slide?
Yes, so you say the derivative, but this was a ternary relation. So maybe there are many df's that could be in relation. So it's not the derivative, it's kind of some derivative. Or...
Yeah, it is technically a derivative, not the derivative.
Okay.
Yeah.
Okay.
Derivatives will not turn out to be unique under this notion of derivative. So let's suppose that we have a function step and a derivative for it, step prime, right? So if step turns sets into stets and we're trying to find its fixed point, step prime will take, as it were, a known world, a set so far, a frontier, and it will produce the updated frontier. And so we want to find the iterations of the step function, a sequence of known worlds, and then we will do that using a sequence of frontiers dr sub I, each one of which is going to be a change from Ri into step applied to R sub I. So we're going to do this by defining these two sequences inductively. R sub 0 is a gimme, it's the empty set. Dr sub 0 will end up being step of the empty set, because you can see that the empty set union step of the empty set will be step of the empty set, which is exactly what we want. We want dr sub 0 to turn R sub 0, the empty set, into step of the empty set. And that will be the only time that we need to call step. The whole point of having these changes is that we can apply them to find the next known world. And we find the next change using our derivative. We tell it, look, step, your input has increased from Ri by dr sub I. So tell me what your output is, how your output has changed. And that's it. This is the core idea of semi-naive evaluation. If you have a derivative for a function, you can iteratively find a fixed point without repeatedly calling the function itself.
Do we even need to call it once? Could we call, in the first line, could it be step prime of, I don't know, the empty set in R0?
That would be step prime empty set, empty set. So it would be, how does the function step change as its input changes from the empty set to the empty set?
Oh.
Which would do nothing.
No, that can't be right.
So I don't see any way to avoid calling step once.
Okay.
At least not without having access to step's source code, which, as it turns out, we do. So there might be something clever you could do. Okay, but for now, I'll settle for just calling step once. So for putting this idea into practice, we actually use two static transformations on expressions, one of which says, okay, look, to find fixed points faster, we need the derivative of the function we're taking the fixed point of. To find its derivative, we need the derivatives of the function it calls and the derivative of functions they call and so forth. So phi annotates all the functions that a fixed point uses with their derivatives. And the sort of technical detail we use to do that is we propagate these derivatives by hijacking the box comonad, by reinterpreting it. I won't go into that as it's somewhat full of technical details. So for that, you should see the Popple 2020 paper. Delta E, so we also need to find these derivatives, not just annotate things with their derivatives. For that, we use delta E, which computes how phi E changes as its free variables change. And the key idea here is to propagate the changes for each variable. So for each variable in your source program, there will end up being two variables, the original variable and the change to it. And I'll give some examples of that on the next slide. And then we can show the correctness of these two things using a logical relation that relates them and the original program. The idea is similar to the change relation I showed you before, but more complex to handle the fact that phi actually adds some annotations. For most of the details, see the paper, but let's take a look at the core parts of the delta transformation. So the easiest bit, of course, is how it handles pairs. It does almost nothing at all. It just distributes over pairs, right? So this is just, what is the derivative of E1 comma E2? Well, it's how does the first bit change and how does the second bit change? How does the projection change? Well, project out the part of the relevant change. Okay, but what about functions? Well, we already covered the fact that functions let you incrementalize function application, right? So if we want to know how a function application changes, we take the derivative, which takes an original input and a change to it and produces the change in the output. We feed it the original input. These brackets are just for monotonicity type checking, and we feed it the change to that input. Dually, what do we do for lambdas? Well, our original lambda took one argument, so we're going to need a lambda that takes two arguments, or two lambdas, which means this thing introduced one variable. This is going to introduce two, x standing for the original input and dx standing for the updated input. So where E, for every free variable E has, delta E will have two.
So I should understand delta as a sort of source-to-source program transformation.
Yes.
Yeah.
Yeah. Delta is a source
You're
transformation.
going to push it down to the leaves and it's going to disappear altogether.
Yes, exactly.
Right.
And speaking of leaves, right? This tells us how we should deal with x, with variables. We just turn them into the corresponding change variable. Right? So every function becomes a binary function, taking an original value and a change. Every variable splits in two, the original value and the change. And when we encounter changes, we just give back the change variable.
Can you just remind us why we have a box on the A in the top line?
Right.
Yeah,
so, yeah. So that's because if you think about the behavior of the change to a function, it will be monotone with respect to the input change. If you give it a larger change to the input, you'll see a larger change in the output.
Mm-hmm.
But it will not necessarily be monotone with respect to the base point. If you increase the base point, the change might actually decrease.
Mm-hmm.
And that's what that box is there for. It's saying it's not monotone in this argument.
Thanks.
Yeah. And then the rest of this is basically for every operation in your language, you need to figure out what its derivative is, how it responds to changes, right? So it's a simple example, right? How does union, right? We deal with sets a lot. A basic operation on sets is union. How does the union of two sets change? For us, it just changes by taking the union of the changes, right? We want to know what got added to E1 union E2. Well, it's whatever you added to E1 and whatever you added to E2. All right. So that's basically all that I have to talk about incrementalizing fixed points.
Michael, could I ask a question? So I know that, so it's not particularly my area, but I know that differentiable programming is quite a big deal. I mean, maybe not specifically in this domain. Could you just tell me a bit about how this is related to maybe similar languages or dissimilar languages where people have added in a similar sort of differential operator?
Well, so this is basically directly based on the work, line of work called the incremental lambda calculus.
Okay.
Which is not, so you mentioned differential programming, and this is not differential programming. It's more like finite differencing. Because we're not asking how things change, with respect to infinitesimal change.
There's no infinitesimals here, yeah.
Yeah. Everything here is finite. Everything here is actual, data flowing around. No smoothness, no infinitesimals, no continuity. There are probably some similarities even so. I wish I were more familiar with the differential programming literature and then I could say something more intelligent.
I mean, ultimately, even in the sort of numerical programming, differential programming world, they don't have real numbers. They have machine floats, so everything is discrete. And I wouldn't be surprised if there was some connection, right, between these change types and the differential types at some level. But anyway, thanks for reminding me of that background.
It's possible.
But what you're describing is strikingly similar to the way source-to-source transformation for forward automatic differentiation. I'm sure, as I know.
Sorry, if I can interject here. So I think I might actually be the right person to answer this question, because my entire thesis, the point of my entire thesis was to take these techniques for incremental computation and see how close they can get to actual real analysis. And what we found was that there are models of systems like this that you can actually interpret in real numbers and infinitesimals. And what you get is that this source-to-source transformation that you see here is exactly, literally forward mode AD. And if you want to, given enough extra hypotheses, you can actually reframe this syntactic transformation in terms of like multiplying by an infinitesimal. So if you're interested in the differential sides, just let me know, and I'll talk your ear off, because it's all I do.
Let me add one thing as well. So the thing Michael is doing is not the differential lambda calculus, and that's actually like crucial. So at the bottom of his slide, he has the derivative, the incrementalization of E1 union E2 is the union of the changes, and there's actually a lot of freedom here. So if you thought of the exact change would be whatever the change to E1 minus whatever was already in E2 plus the change to E2 minus whatever was already in E1. And you would need that if you wanted to have like a sort of exact unique differential. And for efficiency purposes, you really don't want to do set differences. And so the thing Michael is doing really critically exploits the freedom to not be a derivative.
Okay, thanks for that great discussion. Do you want to continue, Michael? Michael, I have to leave in a couple of minutes to take my children to school. Andy will kindly finish off the sharing. So my apologies for having to leave early. Please
All right.
continue.
No problem. Does someone know how to turn off the recording?
Don't worry, that will happen. I'll sort that out when I get back. I'll just leave it on and then I'll trim it. I'll sort it out later. Yeah. Thanks for asking about that.
Okay. Yeah, that was a great discussion. I was just going to mention that Mario might want to pipe up. So thank you. Right. So roughly the ideas are monotone, bottom-up monotone fixed points are actually really nice. I only showed a very trivial example, which was reachability in a graph, but these are actually used in practice. As I said, I know them be used for static analysis in the wild in industry. You can express parsing and regular expression matching in shortest paths in terms of them. And we have examples of some of those in our papers. To compute them efficiently, you really need to incrementalize the step function, especially if you have a large number of iterations. This can asymptotically increase your efficiency. And you do that by propagating changes through your program, which, as people have pointed out, looks a lot like and is in some sense the same as forward mode AD. I'd be interested to know what is the relationship, like what would reverse mode AD be in this context? Maybe we can talk about that afterwards. But I would like to, if I have time, try to get on to concurrency. We'll see how far we can get. So stop sharing over here. Start sharing over here. At some point this should work. Oh, there we go. It always takes a little longer than I expect. Okay, can everybody see this?
Yes, looks great.
Okay, great. All right, so the first bit of this talk was about incrementalizing fixed points, but this incremental fixed point is still fundamentally single-threaded. You're still iterating on a single piece of state until it hits the value you want. How do you make that better? Well, I don't have the full story, but I do have some ideas about how to use concurrency. So first, let's take a look at our previous example of the function we were iterating, this step function. So we want to solve for r equals step r, find a fixed point of it. And as a first step, I'm going to rewrite this in graphical notation. I'm going to make it a little graph. We have this entire subcomponent I'm going to call the neighbors component because it finds the neighbors of the set R, right? The things which R has edges into, right? And so if we write this step function as a little graph, we have, right, our nodes are going to be functions. Here's a node that computes the union. It corresponds to this union operator. Here's a node that just computes the singleton set start and feeds it into union. And here's the node that computes neighbors. Okay, so there's our function represented as a graph, but we're trying to find a fixed point. We're trying to make this edge, this output, equal to this input. So, well, we may as well represent that by tying a little loop. So we've tied a little loop and said the output of this is equal to the input of that. And we're also going to duplicate this output over here because we actually want to know what the eventual result is. So this is our output to the external world. So this is all very well as a representation of what we want to do, but can we actually compute with it?
We don't need to union start in every time, do we?
No, but yeah, that's the insight that leads to incremental computation. I'm chasing a different insight right now.
Okay.
So, right, let's take a look at trying to actually execute this program. Although that insight will also turn up when we try to execute this program. So the way we're going to execute this program is we are going to assign each edge a value. Initially, the values are going to be the empty set. All of these functions operate on sets. We're going to start with the empty set because it's sort of the least possible value. Every step, we're going to pick some nodes to evaluate. We're going to evaluate them on their current inputs, the values coming at them on their input edges. We're going to update their outputs simultaneously. And then we're going to repeat until there is nothing left to be done. And you'll notice that I haven't said how we pick the node to evaluate. We can do it any old way we like. So maybe I pick the union node to evaluate. Well, what's the union of the empty set and the empty set? It's the empty set. So we shove the empty set onto the outputs. But it's already there. They were already the empty set. So we could evaluate this node, but it would be useless. It would not do any useful work. So what node can we pick that would do something useful? Anything? Well, the only node we can pick is start, right? Picking neighbors, the neighbors of the empty set is also the empty set. So we pick start, we update its output, and it sends start on its little edge. And now we repeat. We pick some node to evaluate. Well, now the only useful node to pick is the union node. So we'll pick that. The union of start with the empty set is going to be start. And now there's, again, only one useful node to pick, neighbors. And the neighbors of the start set, well, I don't actually know concretely what that will be, but it'll be whatever the neighbors of the start node are in the graph. And now, again, there's only one useful node to pick, it's union. And at this point, we've actually computed one iteration of step if we run union, because it's the union of the start set with the neighbors of the start set. It's all things reachable in one or fewer steps. And so you'll see that this basically computes the iterations of the step function. So that's interesting. We can rephrase iterating the step function as repeatedly iterating on this graph. But what I claim is that once we move to this graph way of thinking, we've actually exposed some useful concurrency. In this problem, we didn't expose, in this graph, there's no useful concurrency, because at each step we could see there was only one node that did useful computation. But let's think about a different way to compute a similar problem. Finding reachability, finding whether a start node, a particular start node can reach a particular end node. So we're going to have thread 1 search for nodes reachable from the start node. Thread 2 search for things reachable from our end node. And they're going to store them in sets A and B respectively. And thread 3 is going to watch these sets and wait until they have a non-empty intersection. And as soon as it sees that there's some node in both sets, some node in the intersection, we can stop, because there's some node reachable from both start and end, which means start can reach end. This is, of course, all assuming the graph is undirected. You can do a similar thing if it's directed, but whatever. Okay, so how do we code this up as a graph, as a program graph? Well, we can do it like this. We can use 2 copies of our little fixed point loop from before. This one searches for nodes reachable from start. This one searches for nodes reachable from end. And then we take their union and ask whether it's not empty. And although this fixed point loop has no useful concurrency, there's only ever going to be one node in it that's doing useful work. And similarly for this one, we have 2 of them. So there might be 2 nodes capable of doing useful work. So we've exposed some concurrency. Yeah, I think I have time for a larger example. What if we wanted to expose more concurrency, as much concurrency as there is in the problem? Well, let's suppose that the graph we're trying to compute reachability on looks like this. We can model our program graph after our data graph and expose as much concurrency as there are nodes in the graph. And the way we'll do that looks like this. We're going to turn every node in our graph into a program node. And it's going to be computing a set that contains up to 2 elements. A symbol start, meaning that this node is reachable from the start node, and a symbol end, meaning this node is reachable from the end node. And it's going to compute these by just talking to its neighbors in both directions. So this node is reachable from start. if and only if this one is, so they talk both ways. And all we have to do is say, okay, we better make sure this node, which is our start node, knows that it's reachable from start. So we'll send it a little start message. And we better make sure this node knows that it's reachable from end. And then this knowledge will just propagate, right? In no particular order, because we're picking things, in no particular order, non-deterministically, but it will propagate through this graph. And then we have one final sync node, a listener, that asks, are any of these nodes, right? All of these nodes, send me your states. Are any of them the set start, comma, end that say I am reachable from both start and end? If so, we're done, right? So that just sends the result of that question. And here you could
just like blue paint, ink blotting out from one end, and green paint, ink blotting out from the other, and then the nodes complain if they see both.
Exactly.
Mm-hmm.
All right, so I call this double-ended flood fill for exactly that reason. Mm-hmm. And this is as concurrent as, as many threads can work on this as you have nodes in your graph. They're not doing very complex computation, but they are all working independently. Okay, so at this point, we have something extremely concurrent and non-deterministic. So does the order in which we evaluate things, in which we execute nodes, matter? And how do we reason about these programs? So what I'm going to do is present a simple, well, relatively simple semantics for these program graphs. To do that, I'm going to have to be a little more precise about what my ground rules are. I've been following some unstated rules when constructing these graphs. So each edge is going to have an associated type, which is going to be a pointed poset. In all our previous examples, these were sets, but they don't have to be, right? They just have to be drawn from some partially ordered set, and it has to have a least element. That's what I mean when I say that it's pointed. So for sets, this was the empty set. For Booleans, it could be false. For the natural numbers ordered 0 below 1 below 2, this would be 0. Each node is going to be a monotone map. So I didn't state this, but it is critical. Your node functions must be monotone. Otherwise, determinism is out the window. It does matter what order you do things in. A state is an assignment of each edge to a value of the appropriate type. And the initial state is just going to assign everything to bottom, right? Which we know, bottom meaning the least value of that type. Okay, so given these ground rules, does order matter? It seems like it does. So let's take a look at this. I've copied the same program out twice. Let's try running it with two different schedulings, two different choices of which nodes we evaluate when. On the left, I'm going to evaluate every node all the time. On the right, I'm going to evaluate the identity node only at odd iterations. Right, so the nodes here are +1. So I'm working with numbers here rather than sets. This adds 1. This is the identity function. Let's see what happens. And this is our output. And I'm going to write a little list of all the things we generate. So, okay, first step, we replace the identity function runs. Its input is 0, produces 0. This function +1 runs. Well, its input is 0, so it produces 1. And our output is 0 for this step. Over here, we do the same thing, but we do this exactly the same thing, actually. Right, so far so good. Now we're going to, again, run every node on the left-hand side, but on the right-hand side, we're not going to run the identity node. So +1, the identity node copies its input 1. That means one of our outputs is 1. The +1 node increments its input. We get 2. Okay, same thing over here, except that the identity node doesn't run, so our output stays 0. So already our outputs have diverged, right? At step 1, the one on the left produced a 1. That's a 1, even though it looks like a 2. And the one on the right produced a 0. Let's see what happens as we keep doing it, right? So this will copy down to 2. This will increment to 3. This will actually run this time, so it will copy down to 2 because this is an odd step. This will increment to 3, 2, 2. And if we keep running this, you'll see that the one on the left is just generating the natural numbers. While the one on the right is generating the even natural numbers because it only copies, the id node only runs once every other step.
So for you, the semantics of the program is the sequence of outputs that appear on a node, not the final values after it's settled down.
Then they're different.
But that, I mean, you could choose a different semantics, which is to do the ink blotting and wait till it's all stable and only then report.
I am going to choose a different semantics, but it's not that one.
Okay.
Right, so this, and I won't bother to do the other steps, but you can see. So over here, right, this one is computing the naturals, this one is computing evens. As streams, as values changing over time, these are not equal. But they have the following interesting property, right? And the reason why I'm not choosing to wait until quiescence is because I want to allow these programs, and these programs never hit a final value. They just keep increasing. So
why do you want to allow these programs?
Well, for one thing, it makes it more obvious how to deal with open programs, programs that receive input from the outside world. You don't want to assume that the outside world stops changing. And for another, the semantics I give will end up being a strict generalization of the semantics that waits for quiescence. So it will have as a corollary that if it quiesces, then it's well behaved.
But you're moving beyond the monotone functions and fixed points.
Yes.
Okay.
Well, sort of. Yes.
Well, beyond fixed points anyway. You've still got monotone functions. Fine. Thanks.
In a sense, we are finding a fixed point. I'll get to that later.
Ooh.
So, right, these are not equal as streams, but they do have the property that every value in the natural numbers is eventually exceeded by some value in the even numbers. For everything that one produces, the other eventually exceeds it, and vice versa. So let's think about this ordering, this semantics. Let's take streams, right? And our streams are going to be monotone, right? They're going to be increasing over time. And let's order streams according to this ordering. We say that a stream X is below a stream Y if for every time I, there is a time J such that X at time I is below Y at time J. Everything X attains, Y eventually exceeds. For lack of a better name, I call this ordering Harry. This is the Harry ordering on posets. And if you take—
Why?
I needed a name. I was talking with a friend about it. We picked the name Harry for, I don't remember why. It was my friend who picked the name.
Thank you for that answer.
And I have yet to hear a better name for it. If you have a name, I would be interested to hear about it. But for now, this is what I'm calling them. All right. So we have this order. This order is reflexive.
I'm sure there's a suitable formula in temporal logic that you can use as a name, can't you? Involving some letters.
Possibly.
Yeah.
Oh, that's an interesting idea.
Or possibly a logician from the 1930s or 40s who had the first name Harry.
I mean, I'm sure there's a name for it somewhere, but anyway, this is what I've got. So this ordering is reflexive. A thing is below itself and it's transitive, but it is not anti-symmetric on streams, right? You can have two streams like the naturals and the evens that are equivalent but not equal. If we take the equivalence classes, that's what I call Harrys, right? So then once we have these, we can actually start saying in what sense these graphs are deterministic, right? So if you have a graph and we're going to generalize it to allow some inputs from the outside world and some outputs to the outside world. So the graph has an internal state and also takes inputs and outputs. To execute a graph, well, give me the graph, tell me at each time what the inputs are, and tell me what your schedule is when you're, which nodes you're evaluating at each time step, and I'll tell you what the output stream is, right? So that's clearly fine, but it's still dependent on this schedule. Different schedules will lead to different results. But we have the following theorem. If you give me any two fair schedules, what I mean by fair, I mean it doesn't starve any nodes, right? Or more precisely, it executes every node infinitely often eventually. And this is just because, look, if you're willing to starve a node, you can halt the computation if you want to, right? I mean, you can't do anything useful if your scheduler refuses to run a node. Okay, so if you have fair schedules, and if you give me two streams, one of which is below the other according to the Harry ordering, then execution is actually monotone with respect to this Harry ordering. The output of executing the graph on the first stream, X with a scheduling S, is below in the Harry order, is eventually exceeded by the result of executing on the second larger stream with another fair scheduling. Any other fair scheduling. Doesn't have to be the same scheduling. And this gives us our determinism result, because in particular it means, right, if your input streams are equivalent, then your output streams are equivalent no matter the scheduling you use. So the scheduling is irrelevant up to Harry equivalence. And as a consequence, right, if it reaches a fixed point, that means the stream is going to stop increasing at some point, right? And two streams that both stop increasing are only Harry equivalent if they stop increasing at the same value, right? So this gives us our quiescence criterion. It tells you, look, if one execution quiesces, they all do. And so the semantics of these graphs is that they're Harry transformers. And yeah, it looks like I'm just about out of time. I will just make a few final notes. I came across Harry's just by figuring out the order on streams that seem to be respected here, but they do have a sort of categorical way of thinking about them. They turn out to be the free omega CPO on a poset. That is to say, if you take omega CPOs, omega complete partial orders, Harry's turn out to be omega complete, which is non-obvious and which I'm not going to explain because I don't have time. But every omega CPO is clearly a poset, has a partial order. There is a left adjoint to this forgetful functor from omega CPO to poset, and it is precisely Harry, right? It takes a poset into the poset of Harry's, the omega CPO of Harry's on it. And Harry transformers turn out to be exactly the same as omega continuous maps between Harry's. So it turns out we were doing domain theory all along, and the thing that you are computing when you ask for the behavior of one of these graphs over time, while it may not be the fixed point of the functions involved, it is the fixed point of the Harry transformer, right? So there is a fixed point being computed here. It's just being computed differently than you might expect. And that is that, except for noting that I have these two stories, incrementally computing fixed points by doing the derivative and propagating changes through, and concurrently computing them by having these graphs and scheduling them however you like, and then being guaranteed the answer is going to be the same in the end anyways. I have no idea how to reconcile these two stories. It is not obvious how to take a graph and compute it incrementally.
So, Michael, I did want to, thanks for that. That was very interesting. I did want to say something there. I have to pop off quickly, so I'll be brief. But I don't know if you've talked to the folks at SEML recently, but they have, obviously a practical, very practical data log evaluator that I know now does quite a lot of parallel evaluation. And I don't think it looks like your strategy, but it certainly looks like a strategy. And I think that, particularly if you're interested in kind of tying it to some practical stuff, I'm sure there would be something to say about why the parallel strategy that they use is semantically correct, right, and doesn't actually ruin anything. I don't think it looks quite like what you're doing, but it might be another angle on it, and I think it would definitely be worth talking to them if you haven't. So I don't work there anymore, so I don't know what the state of the art there is now, but I think probably worth ringing them up.
Thank you. I will.
Michael, you definitely chose the wrong first name, Harry. I mean, it's Ed, right? Eventually dominates. Yeah. Does anybody have any more serious comments or questions?
Can I just ask? So let me see if I can formulate the question that's forming in my mind here. You motivated this first incremental improvement by talking about graph reachability, and you said you want to do sort of a linear amount of work rather than a quadratic amount, which the naive evaluation did. Now, another thing you could do, and this doesn't reduce the work from quadratic, is do a sort of all pairs reachability, right? So if I was writing this in data log, instead of computing the set of reachable nodes, I would compute a binary relation, which is the relation y is reachable from x. And this has the advantage that the number of iterations required becomes logarithmic instead of linear, right? So the loop is x is reachable from y if there is some intermediate point z such that z is reachable from x and y is reachable from z. And this is, I mean, in practice, lends itself to higher amount of parallelism. I mean, this is what, I mean, we know that in general, computing the transitive closure of a binary relation is, it's in NC1. So if you do it in parallel, you can do it in a logarithmic number of steps. So I'm just wondering if that lends itself to the kind of concurrency, because your concurrent version was still linear in the number of iterations it needed. You were just halving them, right?
Let me see, the concurrent version.
I mean, essentially, that'll terminate when you find a point in the middle,
right? Which
is, you know, basically the middle point of the shortest path, which is about half the length.
So the one with, as it were, two threads, each searching, one searching from start, one searching from end. That, I think, the number of iterations required will be, as it were, the half the distance of the shortest path. But the amount of work that will be done by those iterations is proportional to how many nodes are reachable in that number of steps, which could be very large.
That's right.
The one that was extremely concurrent, I think, where every node was executing in parallel, I think that's a little more like the one you said. Well, the number of iterations required is still
linear.
No, the number of iterations required is still
that's right. It's still.
But there's also the question, never mind the number of iterations, how much work is actually done.
Yeah, you know, that's, I was trying to make that distinction. I said, what I'm describing is still quadratic amount of work, but the point is, that's what parallelism often does. It reduces the time, but doesn't reduce the work, right? That's, so the computing a binary fixed point seems to reduce the number of iterations to a logarithmic number, but keep but the work is still quadratic. Rather than
sorry, did you say binary or all pairs?
Sorry, I was using those interchangeably. But what I mean is you're computing the binary reachability relation rather than just the set of nodes reachable from a fixed start.
Yeah, although it's also about how you compute that, right? You can also compute that by appending edges one at a time, but the one you're doing is where you append whole paths.
Exactly, yeah.
Right. So yeah, that will certainly compute it in fewer iterations. Each iteration will do more work. You will expose a bunch of parallelism within each iteration. Yeah, there are a bunch of trade-offs here.
Oh, so Michael, this reminds me of, you know, the other thing you didn't talk about, which is the graph cleaning algebra stuff you've been looking at. Because getting the all pairs reachability, if you use like sort of repeated squaring, you'll get it in that logarithmic number of steps.
Yeah, in fact, that's exactly the same thing. You're doing repeated squaring only on a binary matrix. Right, a relation is a matrix with values in Booleans, and composing relations is multiplying matrices. So this repeated squaring until you reach a fixed point, I think, is the same as this the thing Anuj was proposing.
Yeah, so I vaguely remember finding a project called Differential Data Flow somewhere that has a story on concurrency and on differentiability, on how to propagate differentials through one of these computation graphs. Have you seen that so far? And has it been helpful in a way? So is it in any way related to what you've been trying to do?
So it's definitely sort of related in the broad sense in that it's tackling a similar thing. I have looked at that. It's in some sense much more ambitious than what I'm attempting to do. It does not take advantage of monotonicity at all, right? It tries to handle decreasing changes as well. And in order to do that, it needs to have this very interesting notion of multidimensional time. Also, all of its parallelism is sort of lockstep data parallelism, which is certainly possible to do efficiently, but it doesn't have this characteristic of internal non-determinism that the notion of concurrency I'm exploring does. So I would basically say it's trying to address a similar problem, but going at it by a very different route. It's also much more mature work, right? They have a real implementation that people in the industry are using.
Anybody have any other questions?
Yes, so I've waited until everyone had already asked their questions. I think Michael's already expecting this. I have a list.
Go for it. Go for it, Mario.
So my first question, and I think you've already answered this for me in the past, but I forgot. Sorry. You only have one level of deltas, right? Like a set of differences doesn't itself have a set of differences, and you don't want to talk about smooth. Okay. My second question is your box modality suggests that there's a diamond modality that is the fully connected space, and everything that you can do by putting boxes on the left, you can do by putting a diamond on the right.
No, hold on. So, okay, if you do this in pre-order, there are actually 6 modalities. There's identity, which does nothing. There's op, which is for antitone. There's 2 versions of box. There's the one that leaves things that are equivalent to the same, and there's the ones that make everything different. So, if you're right. And then there's 2 versions of diamond. One finds the weakly connected components. So if you have, say, a sum type, A plus B, diamond of A plus B will not be the completely connected thing. It will be just diamond A plus diamond B. And then there's the one that makes everything related to everything else, the indiscrete.
Yeah, that's the one I'm talking about.
I don't think a box on the left is the same as a diamond on the right in that sense, because I remember that box in the weaker sense, not the fully discrete thing, but keeping things equivalent if they're equivalent, that's adjoint to diamond in the weaker sense, the one that distributes over plus. I forget which way it's adjoint though.
Almost certainly diamond would be on the left of box.
Wait.
A function out of it is, yeah, God.
Yeah. Pencil and paper is required.
A function out of a totally discrete space is the same. A monotone function out of a totally discrete space is the same as a monotone function into a totally indiscrete space, in that both of those properties are boring.
Yes.
So I think that's what you were talking about.
Yes, that's exactly what I meant.
Right. Yeah. Yeah, that's true.
I've been calling this like co-discrete spaces, but I have to say indiscrete is a much funnier name. I have a bunch more questions, I'm afraid. Do you ever, because you can use changes to update a value, right?
Yeah.
Do you ever have any cases where you update a function with a change in your actual working system?
Where you update a function with a change? No, I don't think you ever actually apply, like take a function and the change to it and mush them together. You take a change to a function and you apply it to an argument, and the result of that can get applied eventually, but you never directly apply a function to its change. And
another question, sorry, I've been collecting a list. Another question is the parallel stuff that you mentioned at the end is very interesting, but like to me, it seems to suggest that you're sort of moving on a sliding scale where like you have on one end like a graph representation of a imperative program, which is just one node with one loop that is just like it runs, and on the other end it's something that is even further than the last graph you showed, which is just like a non-deterministic, it's literally just a non-deterministic finite automaton. So if you go to the last graph you have and you remove the ending position, the green label into the
hold on,
target
let me
edge.
share the graph.
Right.
Somehow. Where is it? Somewhere in here. This graph?
Yes. Yeah.
Great.
So if you remove the last node completely, and you remove all of the the green one, you remove the green one, and you remove all of the yellow edges except the one that comes from the last the target node. Yes.
Ah, yeah.
What you get is like, and you annotate every edge with just like the empty word. What you get is a non-deterministic finite automaton that computes whether like reachability. So it seems to me that you've probably essentially defined the generalization of non-deterministic automata where you can put data into the nodes, and then you can do this thing where you add more data in each node, and that makes your graph smaller. Does this make any sort of sense?
Sorry, a generalization of non-deterministic finite automata where what?
You instead of a node being either active or not, you can actually have data in a node.
Right,
and so in the sort of like imperative boring program that you had at first, you only have one node, but what that node contains is a set of all of the like nodes that you've visited thus far.
Right.
And so it seems that there is this sort of duality where you can reduce the amount of data that you store in every node by sort of unfolding those computation nodes into these like state nodes.
Yeah.
Does this make any sense? Is this something that you've thought about?
I haven't thought about it in those terms, in terms of finite automata. I have definitely thought about this sort of unfolding process, right? Like, how do you get to this graph starting from the first graph or from the second graph? And I wanted to talk about this, but I decided I didn't have time. But you can sort of say, look, if you have a single edge, which is carrying values from some power set of some finite set, right? Which is what we do here, where our edges typically carry values from some set values. That's the same, or it's isomorphic to, having one edge carrying for every value in your set A, and each edge carrying a Boolean. And so that sort of, and there are nodes, splitter and joiner nodes that mediate this isomorphism. And that lets you diagrammatically reason about those programs by introducing, splitting apart a single edge into many edges, and then taking things on either edge of that thing and mushing the isomorphism across them. So that's what I've thought about.
I think one of the ways of making sense of what I just said is to say, well, if A is just a one element set, then its power set is just either the empty set or the set, the one element itself, which is just 0 or 1. And so your nodes are either off or on, and this is just a non-deterministic automaton, I think.
Yeah. Cool. I had not thought of the connection to NFAs at all.
And sorry, I have one question, one last question, which I promise is the last question, and I stop bothering you. You said that you've applied
these
this
questions
to.
Are great. Good questions.
I'm glad you think so. I hope everyone in the audience is enjoying them as much as you are. So
we have no way of knowing.
You've mentioned that you've applied this to parsing, right? And so in regular expressions, there is such a thing as the derivative of a regular expression.
Yeah.
Do you incrementalize parsing through that idea of the derivative of a regular expression, or is your approach completely different?
Well, we incrementalize it just by applying the transformation that I showed in the semi-naive evaluation bit. I have not thought about whether that, right, and we test that and it works. It increases, it gives you an asymptotic speed increase, basically because computing the star of a regular expression turns out, if you represent matches relationally, to be the same as computing transitive closure. So it speeds it up for the same reason it speeds up transitive closure.
Right.
Whether that is connected with the derivative of a regular expression, I have no idea. Not in an obvious way.
Not in an obvious way, no.
Well, okay, so I don't know. It just seemed to me like maybe the derivative of a regular expression might be the syntactic sort of version of the sort of semantic process that you might be doing. At least I want it to be, but I have no reason to think that it is. But I would like to see that. Because I mean, I did some work on derivatives of regular expressions back in my own thesis, and it turned out to be, it turns out that you can, regular expressions derivatives are derivatives in the same that change structure derivatives are derivatives, so they're derivatives in the same sense. So it would be really cool if you had a theorem that says, well, the semantics of the derivative of regular expression is precisely the derivative of the semantics of the regular expression.
Yeah.
Hopefully.
Very good.
Fingers crossed.
I think at this point, what we should do is we should all unmute ourselves and just give Michael a quick clap. Thank you very much. So Jamie said he was going to turn the recording off when he got back, but it looks like I might have the ability to do that. So I think I'll probably have a...
There's one comment I want to quickly make before you do, if that's okay.
Yeah, sure. Go ahead, Nathaniel.
Vikram and I had a suggestion for a way to rename your Harrys into something else, a bit more conceptual. So we think that this adjunction you have is representing the int completion or the filtered co-completion under omega chains.
That's right. Yes.
In a thin setting. And so I believe there's already an established term for this functor, which is omega ind. So if you want to fit it into an established setting, then there's terminology already out there.
Yeah, so it's
less fun.
It's not Harry, it's wind.
Thank you. I think you sent me some messages about that, but I didn't look at them because I was busy talking to people.
But wind transformer sounds really cool, doesn't it?
Wind transformer. Yes.
Wind transformer, yeah. Well, I think with that, we should call it a day. Thanks, everybody. Hopefully see you next week. I think we've got to, I can't remember who's talking next week. Does anybody remember? Obviously nobody who's still left in the audience otherwise.
I think it might be me.
Oh, well done. Very good. We'll look forward to that. Okay. All right, I'm going to see if I can stop this recording.